July 1st, 1936. Hamburg. Slipway number 9 at Blom and Shipyard. A steel keel is laid down. The first piece of what German engineers intend to be the most survivable warship ever built. They have a plan. Turtleback armor, 19,000 tons of it, angled at 22 degrees inside the hull so that any shell punching through the main belt will ricochet upward and away from the ship's vital organs. At close range, an enemy shell would need to penetrate 640 millimeters of steel, 25 inches, to reach anything that matters. They have done the math, they are certain. May 27th, 1941. North Atlantic. HMS Rodney opens fire from less than 3,000 meters. Her 16-inch guns, the heaviest in the Royal Navy, hit Bismarck again and again and again. 2,800 shells in 90 minutes. The superstructure is erased. Every turret is silenced, but the hull below the waterline is intact. The turtleback armor is holding, exactly as the engineers calculated on slipway number 9 5 years earlier. They were right, and yet Bismarck is going to sink in less than an hour, because everything the engineers got right about the hull, they got wrong about the stern. 2 rudders in 1 compartment. No protection. 1 torpedo. Game over. The men who designed the armor, the 2,800 shells couldn't break, also designed the steering system that 1 torpedo destroyed. This is their story. 21 years before Bismarck's keel was laid, Germany lost everything. The First World War ended not with a bang for the German Navy, but with the most humiliating act a fleet could commit. At Scapa Flow, in the cold waters off Scotland, Germans opened the seacocks of their own warships and watched them sink. 74 ships. Gone. Not defeated in battle, drowned by their own crews, rather than handed over to the victors. And then came Versailles. The Treaty of Versailles did not merely punish Germany's military. It tried to erase it. The army was capped at 100,000 men. The Air Force was abolished entirely, and the Navy, the Reichsmarine, later renamed the Kriegsmarine in 1935, was reduced to a shadow. 6 pre-dreadnought battleships. Ancient, obsolete, relics from before the war. Any replacement vessels were limited to 10,000 tons. 10,000 tons. To put that in perspective, the battleship that would one day become Bismarck would displace more than 4 times that number. But here is what Act Versailles really took from Germany, the thing that mattered more than any ship or gun. It took experience. For nearly 20 years, German naval engineers were forbidden from building capital ships. They could read foreign technical journals. They could send naval attachés abroad. They could study, in theory, what the British and Americans and Japanese were doing. But they could not build. They could not test. They could not make mistakes at full scale and learn from them the way every other major navy in the world was doing throughout the 1920s and 1930s. The last time German engineers had designed and built a frontline battleship and watched it fight was the Bayern class. The last battle those lessons came from was Jutland. May 31st, 1916. 20 years before Bismarck's keel was laid. Every major decision on Bismarck's blueprints can be traced back to that single afternoon in the North Sea. The armor, the guns, the hull, the rudders, all of it. Jutland was the last exam these engineers had taken, and they graduated with honors. The problem was that the curriculum had changed, and no one told them. But we are getting ahead of ourselves. 2 men shaped the strategic world that Bismarck would be born into, and they disagreed on almost everything. The first was Erich Raeder, 65 years old in 1941, Grand Admiral, Commander-in-Chief of the Kriegsmarine since 1928. Raeder was old Navy, through and through. He believed in surface power, big ships, big guns, dominance of the sea lanes. He had served at Jutland himself, aboard the battle cruiser SMS Lützow. He had seen what capital ships could do, and he wanted Germany to have them again. The second was Karl Dönitz, 49 years old, in 1941, commander of the submarine fleet. Dönitz believed the opposite. Surface ships were expensive, vulnerable, and strategic targets that the enemy would hunt relentlessly. Submarines were cheap, numerous, and lethal against the one thing that actually mattered: merchant convoys. Sink enough cargo ships and Britain starves. You did not need a 41,000-ton battleship to do that. You needed 300 U-boats. Raeder and Dönitz were fighting over the same limited pool of steel, labor, and Reichsmarks. Every ton that went into Bismarck was a ton that did not go into a submarine. Every engineer assigned to the Konstruktionsamt's battleship program was an engineer who was not designing a Type 7 U-boat. The engineers who designed Bismarck were working for Raeder's vision. Whether that vision was right, or whether Dönitz had been correct all along, is a question that Bismarck herself would answer, in the worst possible way. But in 1934, Raeder's vision was winning, and the engineers had work to do. The chain of events that created Bismarck began not in a drafting room, but in a loophole. The Treaty of Versailles limited Germany's replacement warships to 10,000 tons. The Washington Naval Treaty limited other nations' heavy cruisers to 10,000 tons and guns no larger than 203 millimeters, 8 inches. Germany was not a signatory to the Washington Treaty, which meant German designers were bound by Versailles' tonnage limit, but not by Washington's gun restriction. They exploited this gap with ruthless ingenuity. The result was the Deutschland class. On paper, 10,000 tons right at the Versailles limit. In reality, closer to 12,000. Armed with 6 280mm guns, 11 inches in 2 triple turrets. Those guns were vastly larger than the 8-inch weapons on every other navy's heavy cruisers. The Deutschland class could outgun any cruiser afloat and outrun any battleship that could outgun them. The international press called them pocket battleships. The engineers who designed them called them a proof of concept. What they proved was that German engineers could turn a limitation into a weapon. 10,000 tons of allowed displacement became the most dangerous cruiser killers on the ocean. This was the first act of genius, not in spite of the constraint, but because of it. The French noticed, and the French were not amused. The Marine Nationale responded with the Dunkirk and Strasbourg. Both displaced over 26,000 tons, more than double the Deutschlands. They carried 8 330mm guns in a striking all-forward arrangement, and they could make 30 knots, fast enough to chase down any pocket battleship and heavy enough to destroy it. Germany's clever loophole had been closed by brute force, so Hitler ordered a response. A larger, faster successor to the Deutschlands that could counter the French threat. That concept evolved through multiple iterations until it became the Scharnhorst class, the stepping stone to Bismarck. But the arms race had its own momentum. Britain, watching Germany and France trade escalations, decided to step in not to stop the race, but to manage it. In 1935, the Anglo-German naval agreement was signed. It allowed the Kriegsmarine to build up to 35% of the Royal Navy's capital ship tonnage. New ships had to comply with the Washington Naval Treaty limits, 35,000 tons maximum. Guns no larger than 406 millimeters, 16 inches. Britain believed this agreement would keep Germany's navy manageable. Britain was wrong. because the engineers were already drawing something that would break every rule in the treaty, and they had been doing it in secret since the spring of 1934. The project had a name designed to attract no attention: Schlachtschiff F. Ersatz Hanover, replacement battleship Hanover, as if the design was simply a routine replacement for the ancient pre-dreadnought Hanover, a ship built in 1907 and long past retirement. It was a lie. The new ship would be 3.5 times larger anything Germany was allowed to build under Versailles. The initial specifications called for a hull displacing 35,000 tons, armed with 330mm guns, 13 inches, designed specifically to counter the French Dunkerques. The main armored belt was set at 350mm, deck armor at 100mm. The engineers were thinking about the North Sea and the Baltic enclosed waters, where engagements would happen at close range. Shells would come in flat, not plunging down from high arcs, so they prioritized the vertical belt, thick side armor. That was the lesson of Jutland, but the numbers did not add up. Calculations showed the design could not stay within 35,000 tons. The belt was reduced to 320mm. That helped. But then came the argument that would define Bismarck, the argument about her guns. In January 1935, at a design conference that would have enormous consequences, the 330mm guns were declared unsatisfactory. The reasoning was blunt. The Bayern-class, Germany's last real battleships, the ones that fought at Jutland, had carried 380mm guns, 15 inches. Why should this new ship be weaker than a vessel built 20 years earlier? Admiral Raeder proposed a compromise. 350mm, 13.8 inches, larger than the Dunkerque's guns, competitive with the latest French and Italian designs. But with these bigger guns, the displacement climbed to 39,000 tons, 4,000 tons over the treaty limit. The engineers now faced a choice that would put them to the bottom of the Atlantic. They could redesign the ship to fit within 35,000 tons. That would mean thinner armor, fewer compartments, a lighter hull. It would mean abandoning the turtleback scheme that Jutland had taught them to trust. Or they could keep the ship they believed was right and lie about the weight. They chose to lie. The official displacement, reported to Britain and to the world, would remain 30,000 tons. The true number, 41,700 tons, would be classified as a state secret. This was the first paradox of the genius engineers. The design philosophy they believed in: distributed armor, turtleback protection, a hull built to survive, could not exist within the rules. Their genius was inseparable from their deception. The ship that would one day take 2,800 shells and refuse to sink was born from a lie about 6,700 tons of hidden steel. But 2 months later, the guns changed again, and this time the decision came not from the engineers or from Raeder. It came from the top. Both the French Richelieu class and the Italian Littorio class had been fitted with 380mm guns, 15 inches, the same caliber as the old Bayern. Raeder, but upgrading the change would delay construction, and war was coming closer. Every month of delay was a month Bismarck would not be ready. He was overruled. Adolf Hitler, 52 years old, in 1941, a man with no naval engineering background whatsoever, personally favored the larger guns. His reason was prestige, not ballistics. Germany's new flagship should not be outgunned by the French or the Italians. The decision was political, pure and simple. And here is where the story takes its first real turn. Because the engineers at Friedrich Krupp AG, the legendary Krupp Steelworks, took a political decision made for the wrong reasons and turned it into one of the finest naval weapons ever manufactured. The SKX C/34, 380 millimeters, 8 of them, housed in pairs, inside 4 massive turrets that the crew would nickname Anton, Bruno, Caesar, and Dora. Each barrel stretched 18.4 meters, 60 feet. Each gun could hurl an 800-kilogram shell at a muzzle velocity of 820 meters per second. Maximum range, 35.5 kilometers, 22 miles. But the real genius was not the size. It was the speed. Thanks to an ammunition hoist system that Krupp engineers had optimized for rapid loading, Bismarck's guns could fire between 2.3 and 3 rounds per minute at a 4-degree elevation that made them among the fastest-firing large-caliber naval rifles ever put to sea. 8 guns, 3 rounds per minute, each 24 shells per minute, 19,200 kilograms of steel and explosive flying down range every 60 seconds. Krupp's shells traveled 8.3% faster than equivalent British shells of the same caliber, at 5,000 meters point-blank range. For a battleship, they could penetrate 616 millimeters of armor. 22 kilometers. At 22 kilometers, they could still punch through 393 millimeters, more than 15 inches. Hitler had demanded bigger guns for reasons of vanity. Krupp's engineers delivered a weapon system that was genuinely, measurably superior. The wrong decision, made for the wrong reason, executed so brilliantly that it became the right decision after all. That was the second paradox. And the engineers were only getting started. The question of why Bismarck carried her guns in twin turrets, rather than triples or quadruples, as the British, French, Italians, Americans, and even Germany's own earlier designs had done, reveals something important about how these engineers thought. The answer was partly technical. Krupp had not yet developed a loading mechanism compact enough to fit 3 380mm guns into a single turret housing. But the engineers saw this limitation as an advantage. Spreading 8 guns across 4 turrets meant that a direct hit on any one turret would knock out only 25% of Bismarck's firepower. A triple turret ship carrying 9 guns in 3 turrets would lose a third. A ship like the French Richelieu, with 8 guns in 2 quadruple turrets, would lose half. There was a real-world example that proved the engineers right. HMS Prince of Wales, a King George V class battleship carrying 10 14-inch guns in 2 quadruple turrets and 1 twin, sailed into battle against Bismarck at the Denmark Strait with turret malfunctions that left her unable to fire more than half her guns. During her retreat, her only remaining turret jammed again. She could not return fire at all. The engineers had also spaced the twin guns far apart within each turret. This reduced in-flight interference between the shells after firing a subtle aerodynamic problem that could degrade accuracy. Each turret rotated at 4 degrees per second. Britain's King George V and Japan's Yamato managed only 2. Only France's Richelieu, at 5 degrees per second, was faster. These turrets were not elegant, they were not innovative. They were a conservative, deliberate choice by engineers who valued redundancy and reliability over raw firepower concentration. And when the guns finally spoke in anger, that choice would prove devastatingly effective. Now the engineers turned to the hull itself, and here the influence of Jutland was visible in every line. European warship design favored a hull shape distinct from American or Japanese practice, where Pacific-oriented navies built ships with a narrow bow, expanding to a wide midship section, and curving into a broad stern optimized for long-range engagements. Across vast ocean distances, European designs tapered both ends. A narrow bow expanded to a wide beam, and then narrowed again to a stern almost as thin as the bow. The shape was built for one thing: stability in the rough, violent waters of the North Atlantic. Bismarck's beam, her maximum width, was 36 meters. Her waterline length was 241.6 meters. The ratio created an exceptionally stable gun platform. Her draft, the depth of hull sitting below the waterline, was just 9.3 meters at standard load. This was among the shallowest drafts for any battleship of her era. Her contemporaries averaged a full meter deeper. The shallow draft allowed Bismarck to transit Germany's coastal canals and waterways, but it also reduced hydrodynamic drag and helped her speed. Her hull form resembled a fast ocean liner, more than a traditional warship. Sleek, long, optimized for cutting through the Atlantic at speed. But that elegance came with a cost the engineers knew about and accepted. When the helm was put hard over a full turn, Bismarck bled up to 65% of her speed. She could not maneuver out of a fight. She was designed to ambush, rush in, fire, disappear at speed, not to dance. The engineers had learned a hard lesson from Bismarck's predecessors. Scharnhorst and Gneisenau had been built with straight stems, vertical bows that cut through waves like a knife, good for maintaining speed in calm water. But in the heavy swells of the North Atlantic, those straight stems plunged directly into wave troughs. Enormous quantities of water crashed over the bow, damaging gun emplacements, flooding equipment, and destabilizing the ship. Both vessels had to be pulled from service and sent into refit to have their straight stems entirely replaced with what designers nicknamed the Atlantic bow, a raked, flared bow that rode over waves instead of knifing through them. Bismarck, originally designed with a straight stem, had the Atlantic bow fitted while still at the equipping pier. The engineers had watched their predecessors fail and corrected before it was too late. Beneath the waterline, they added another refinement, borrowed not from warships, but from civilian engineering. A bulbous bow. Germany had pioneered this feature on the ocean liner Bremen in 1929. The bulb created a pressure wave ahead of the hull that interfered with the ship's natural bow wave, partially cancelling it out. The result was reduced drag, better fuel economy, and a measurable increase in speed. This was genius of a different kind, the willingness to learn across disciplines. Naval engineers borrowing from commercial shipbuilders. Military technology improved by civilian innovation. The bulb on Bismarck was slighter than some of her contemporaries, but it worked. Every fraction of a knot mattered when you were trying to outrun a pursuing fleet. And yet, despite the Atlantic bow and the bulbous forefoot, Bismarck remained a wet ship. During the winter of 1940 into 1941, sea spray so badly damaged the rangefinder in turret Anton that it had to be removed entirely. The engineers had improved the bow. They had not perfected it. Even genius has margin of error. The armor was where Jutland's ghost was most visible. Bismarck's main belt used Krupp cemented armor, Krupp's finest product, face-hardened to 670. Brennel 5.5 times harder than mild steel, with a gradually softening cross-section that reduced spalling damage on the reverse side. 320 millimeters thick, running along 70% of the hull above the waterline. Behind the cemented plate, 50 millimeters of teak wood absorbed shock and prevented fragments from penetrating the ship's vital compartments. But the real signature of the German engineers was below the main belt, the turtleback. The armored deck inside the citadel was not flat. its sides angled downward at 22 degrees, meeting the lower edge of the belt armor, shaped like a turtle's shell. This was a scheme that dated back to pre-dreadnought battleships, refined through the dreadnought era, and carried forward into Bismarck, because the engineers trusted it absolutely. The logic was elegant. At close range, the kind of engagement the engineers expected in the North Sea and North Atlantic shells struck the main belt at a relatively flat trajectory. If a shell punched through 320 millimeters of Krupp cemented armor, it would then meet the angled turtleback. 22 degrees. The effective thickness of the slope increased dramatically from 120 millimeters to a relative 320 millimeters for a shell arriving flat from the side. Total penetration required 640 millimeters of steel, 25 inches. At close range, Bismarck was functionally invulnerable from the side. By the 1930s, most other navies had abandoned the turtleback scheme. British and American engineers had adopted all-or-nothing armor, concentrating the thickest possible protection of vital areas and leaving the rest of the ship essentially unprotected. Their reasoning was that engagement ranges were increasing, fire control systems were improving. The primary threat was now plunging fire shells dropping steeply from long range, striking the deck, not the belt. Against plunging fire, deck armor mattered more than belt armor, and all or nothing allowed designers to make the deck thicker by not wasting tonnage on areas that did not need protection. The German engineers knew about all or nothing. They chose not to use it, because their operational theater was not the Pacific, it was the North Sea and the North Atlantic, where visibility was often poor, where engagements would happen at shorter ranges, and where shells would come in flat. For that environment, turtleback was not outdated. It was optimal. They were right for the war they expected. They were wrong about which war they would actually fight. The citadel, the armored box enclosing Bismarck's magazines and machinery spaces, was further divided by 22 watertight bulkheads. These created what the engineers conceived of as an internal raft. Even if the extreme ends of the ship were torn open and flooded, the citadel would maintain buoyancy. The ship could lose her bow and her stern and still float. The torpedo protection system extended this philosophy below the waterline. A torpedo belt ran along the hull, 45 millimeters of plating, spaced 5.5 meters from the inner hull, at its widest point, tapering to 3 meters at the extremities. 2 longitudinal walls divided this space into 3 layers. The outer void absorbed the initial blast. The inner compartments, filled with fuel oil or water, dampened the shockwave and caught shrapnel. A degaussing cable ran nearly the full length of the hull, the MES system, reducing Bismarck's magnetic signature to protect against magnetic mines and magnetically fused torpedoes. In total, 19,000 tons of armor made up 40% of Bismarck's combat displacement. The deck armor alone weighed 6,541 tons. It was heavy, it was high in the hull, and it required a wide beam to maintain stability. Every design choice cascaded into the next. Nothing existed in isolation. The engineers understood this. They built the hull wide enough to carry the weight. They accepted the speed loss in turns because Bismarck was not meant to turn sharply in combat. They accepted the thinner deck because they did not expect to fight at ranges where plunging fire was the primary threat. And then there were the rudders. 2 small rudders, each 8 degrees from the center line, positioned between the outboard propellers and the central shaft. 2 small rudders were more hydrodynamically efficient than 1 large unit less drag through the water. In a turn, Bismarck listed only 3 degrees, an excellent result. The engineers were satisfied, but the two rudders were placed close together, in the same compartment, with no special armor protection beyond the standard hull plating. The engineers had designed the most elaborate torpedo protection system of its era to shield the sides of the ship. 5.5 meters of layered defense, void spaces, fuel-filled compartments, shock absorption. The sides were fortress-like. The stern had none of this. Why? Because at Jutland, no battleship had lost its steering to an aerial torpedo. Because in 1916, torpedo-carrying aircraft did not exist as a significant tactical weapon. The engineers designed the torpedoes for the threat they knew torpedoes launched from ships and submarines striking the broadside. They allocated their protection budget accordingly. Sides, maximum. Stern, minimum. It was not stupidity. It was the boundary of their experience. The same Jutland that taught them to build a turtleback that 2,800 shells could not penetrate also taught them that stern protection was unnecessary. The genius and the fatal flaw came from the same classroom. Deep inside the hull, the engineers chose reliability over innovation for the power plant. The original specification called for a turboelectric propulsion system, massive steam turbines driving electric motors, theoretically capable of producing 46,000 shaft horsepower per unit. But turboelectric systems were enormously heavy, and the engineers, already fighting a tonnage battle with the armor, could not afford the weight. The system was dropped. In its place, they installed high-pressure geared steam turbines, a technology Germany knew well and trusted. 3 sets, built by Blom and Voss themselves. Each drove a 3-bladed propeller, 4.7 meters in diameter. The 3-shaft arrangement was a German tradition going back to the König class of 1916. German engineers had calculated that a 3-shaft ship enjoyed roughly 6% greater propulsion efficiency than a 4-shaft equivalent. The engines worked less to maintain the same speed. Fewer shafts also meant less weight and simpler maintenance. 12 oil-fired, ultra-high-pressure water tube boilers, built by Wagner in Hamburg, fed the turbines, distributed across 6 boiler rooms, each watered, compartmented against battle damage. These boilers produced steam at 825 pounds per square inch, and temperatures reaching 450 degrees Celsius. Enormous pressure, enormous heat, enormous power. On October 23, 1940, during speed trials in the Baltic, the engineers held their breath as the turbines were pushed to their limits. 150,170 shaft horsepower. The propellers spun at 270 revolutions per minute, not far off from a destroyer's props. For comparison, the American Iowa class, often considered the fastest battleships ever built, turned their propellers at 106 RPM at equivalent speed. Bismarck hit 30.1 knots on the measured mile. Her contract speed had been 29. The engineers had delivered an extra knot, and in a stern chase across the Atlantic, 1 knot could mean the difference between killing and destruction. With a maximum fuel capacity of 7,400 tons of oil, Bismarck had a cruising range of about 8,800 nautical miles at 19 knots. But speed consumed fuel exponentially. At 30 knots, that range shrank dramatically, and the fuel system had its own hidden weakness. The forward oil tanks had no cross-connection valves to the main system. If those tanks were damaged or cut off, the fuel inside them was simply lost, gone, irreplaceable at sea. The engineers had designed a ship that could outrun almost anything afloat. They had also designed a fuel system with a single point of failure that no one noticed until it was too late. The guns were ready. The armor was in place. The engines could push 30 knots. But Bismarck needed to see her targets before she could kill them. And what the engineers built for her eyes was a system of extraordinary sophistication, sitting inside a body of frustrating limitation. The fire control system was built around stereoscopic rangefinders, manufactured by Zeiss, the legendary optics house. 3 command stations mounted rangefinders of 10.5 meters, 34.5 feet, with the forward station carrying an additional 7-meter unit. Each of the 4 main turrets also had its own 10.5-meter rangefinder for independent, local control if the central stations were knocked out. This redundancy was deliberate. German doctrine required Bismarck to engage 2 separate targets simultaneously with equal firepower. The paired C/38 fire control computers, 2 forward, 2 aft, made this possible. One in each pair computed solutions for the main 380mm battery. The other handled the secondary 150mm guns. If one computer was destroyed, the other could switch roles by simply changing the ballistic data input. If an entire computer room was wrecked, the surviving room took over everything. The C-38 automatically adjusted for weather, barometric pressure, and barrel heating from sustained fire variables that would shift a shell's trajectory by dozens of meters at range. Operators monitored the solutions on photoelectric CRT displays, technology that looked futuristic even by 1941 standards. For close-range gunnery, the kind the engineers expected, this system was devastating. Zeiss optics could pinpoint a target with unmatched clarity. The C/38 could compute a firing solution faster than any human crew working manual calculations. But bolted to the same command stations was the Fumo 23 radar, 2 meters high, 4 meters wide. Germany's finest radar in 1941. Its maximum effective range was 25 kilometers, 15.5 miles. And it lacked a plan position indicator display. No PPI meant the radar could track only one target at a time. It could not show the operator a map of everything around the ship. It gave range and bearing to a single contact, nothing more. The British Type 273 and Type 281 radar sets could detect targets at over 40 kilometers, and they had PPI displays. The difference was not marginal, it was generational. Bismarck had the finest eyes in the world for aiming her guns. She was nearly blind for understanding the battlefield around her. The engineers who built the rangefinders were geniuses. The engineers who built the radar were a generation behind. Both worked on the same ship. Both failures and triumphs would reveal themselves on the same day. Then there were the weapons the engineers got wrong, and they knew it. Bismarck's anti-aircraft armament consisted of 16 105mm dual-purpose guns in 8 twin mountings. They were hand-loaded, 18 rounds per minute, guided by 4 dedicated fire control directors that were electronically stabilized when they worked. They frequently did not. Internal reports filed before Bismarck ever sailed into combat contained language that should have alarmed everyone who read them. One report noted that the 2 different mount types, the C/31 and C/37, created considerable operational disadvantages. Another stated plainly that firing at sea targets or low-flying aircraft using the 105mm gun in the C/37 twin mounting was practically impossible by direct aiming. Practically impossible. The engineer's own assessment, before the ship ever faced a hostile aircraft. Below the dual-purpose guns sat 1637mm flak guns, C/30 types, also hand-loaded. 30 rounds per minute. In combat, they proved sluggish. They were replaced fleet-wide by automatic versions in 1942 and 1943. For Bismarck, that upgrade would come too late. 20-20mm automatic cannons rounded out the close-range defense, fed by 20-round magazines. A theoretical rate of fire of 120 rounds per minute, but constant reloading cut that dramatically. Even the four-barreled mounts could only put 80 rounds into the air between magazine changes. The engineers understood, by 1940, that aircraft were becoming a serious threat. But in early 1941, the full power of naval aviation had not yet been demonstrated. No European battleship went to sea with impressive anti-aircraft capabilities. The engineers designed Bismarck's air defenses for the threat level they perceived, and that perception was about to be proven catastrophically wrong by a biplane made of fabric and wire. Bismarck carried 3 types of main battery ammunition, each designed by Krupp's engineers for a specific target. The Panzergranate 4.4 Mitty Hobie armor-piercing, painted blue. This was the ship killer. An aerodynamic cap helped it fly at maximum velocity. A delayed fuse let the shell punch through armor and detonate inside the target 20.3 kilograms of TNT equivalent deep in the enemy's vitals. 350 of these shells were carried aboard. The Sprenggranate L4.5, with base detonating fuse, high explosive, painted yellow. Less penetration, but 35 kilograms of TNT, designed for cruisers and destroyers. The delayed fuse let it punch through light armor before detonating. And the Granate L4.6, Kopfzunder high explosive with a nose contact fuse, 62.8 kilograms of TNT, nearly 140 pounds, double the explosive charge of the L4.5. It detonated on impact, spraying superstructures with a storm of burning shrapnel. Against unarmored merchant ships, a single hit from a Kopfzunder could be fatal. 2 or 3 could send a moderate-sized freighter to the bottom. Each shell was propelled by a 2-part charge, a 4 charge of approximately 100 kilograms of propellant, packed in a silk bag, and a main charge of 111.5 kilograms in a brass casing. After every shot, the spent brass was ejected out the back of the turret. After a battle, spent casings would be rolling across the deck like debris at a firing range. It was inelegant, but it kept the loading cycle fast, and speed was everything. Bismarck's secondary battery gave her the firepower of a light cruiser on top of her main armament. 12 150mm guns in 6 twin turrets, 3 per side, derived from the main guns of the Königsberg and Leipzig-class cruisers. Each mount weighed 120 tons, range 23 kilometers, rate of fire 8 rounds per minute. These were surface-only weapons, not dual-purpose. They could harass heavy warships by starting fires in ammunition lockers and exposed equipment, or they could shred destroyers and freighters with armor-piercing shells. Against an unescorted convoy, Bismarck's secondaries alone would have been devastating. At the stern, the engineers had installed 2 features that revealed just how thoroughly they had thought about Bismarck's role as a commerce raider. A chemical smoke generator contained canisters of chlorosulfuric acid. Each canister could produce 20 minutes of dense concealing mist as the acid vaporized and absorbed moisture from the air. The toxic fog was sprayed directly from the stern through 2 small ports, a screen for retreat, and on the fantail sat 2 racks of depth charges, 9 in total. Depth charges on a battleship seemed absurd. Bismarck could never catch a submarine. But the theory never confirmed in action was that the charges could be dropped behind the ship, Shrikathav's engagement to create artificial water columns. Enemy gunnery officers, seeing the splashes, might think their shells were falling short and overcorrect their aim, shooting over Bismarck instead of into her. On May 26, 1941, 3 of these charges were accidentally knocked overboard by the concussive blast of Bismarck's own main guns firing. Whether they ever would have worked as intended remains unknown. 4 Arado AR-196 float planes sat aboard for reconnaissance, 2 in hangars abreast the funnels, 2 on or near the catapult. They were nimble machines with folding wings, powered by the same BMW engine used in the 4-engine Focke-Wulf Condor bomber. Maintained by Luftwaffe personnel Air Force men embedded within a Navy crew, a peculiarity of the German military's divided command structure. A compressed air catapult launched them, and the ship's main cranes retrieved them from the water after landing. The engineers had designed a hunter, speed to rush in, guns to kill, smoke to disappear, armor to survive retaliation, reconnaissance aircraft to find targets, depth charges to confuse pursuers. Every system served a single tactical concept: strike hard, strike fast, and vanish before the enemy can concentrate his forces. 2,200 men would live inside this machine. 12 divisions, each with a specific function: gunnery, engineering, signals, radio, carpentry, even cobblers and tailors, because a ship this size was a floating city that needed to clothe and shoe its population. Officers included the captain and his bridge staff, the executive officer, the navigation officer, the chief engineer, gunnery officers for the main, secondary, and anti-aircraft batteries. The admiral's fleet staff added a chief of staff, a Luftwaffe liaison officer, and a fleet physician. The sailors in hammocks, slung from the deckheads. Simple metal lockers held their possessions. A vast network of ventilation ducts, rarely seen in photographs but visible in surviving engineering plans, snaked through the interior, drawing fresh air in and pushing stale air out. Even something as mundane as keeping the air breathable aboard a ship this size required serious engineering. On the 1st of July, 1936, the keel was laid at Blohm and Voss, slipway number 9, Hamburg. The shipyard's workers made a decision that would save Bismarck's life. 5 years later, they welded 90% of the hull instead of riveting it. This was not standard practice. Riveting was traditional, reliable, but heavy. A ship the size of Bismarck would need over 10 million rivets, adding more than 1,500 tons of weight. And riveted plates needed to overlap, using more material. Welding eliminated both problems. A welded joint was a continuous bond, roughly as strong as the steel plates it connected. Riveted seams under the shock of battle could pop open and let the sea in. Welded seams would hold. From the bottom up, the engineers and workers built her. October 1937, the turtleback citadel and armor began to take shape. Mid-1938, the barbettes rose from the hull, tall steel cylinders armored up to 340 millimeters above the upper deck. 5 months before launch, the hull reached the main deck. February 14,939, a jubilant day. In Hamburg, Adolf Hitler delivered a speech. Dorothy von Lohenfeld, 47 years old, granddaughter of the statesman Otto von Bismarck, swung the bottle and christened the ship with her grandfather's name. 241 meters of steel slid down slipway number 9 and into history. 3 years of construction, hundreds of thousands of man-hours, 41,000 tons of steel, 197 million Reichsmarks. The empty hull was towed to the equipping pier. Engines and boilers were sealed deep within. The superstructure rose. The rangefinders were mounted. The guns were installed. Slowly, she started to resemble what she was, the most powerful surface warship in European waters. On August 24th, 1940, Bismarck was commissioned into the Kriegsmarine. Her captain was Ernst Lindemann, 47 years old, a gunnery specialist who understood Bismarck's systems better than anyone aboard. He was so proud of his ship that he insisted on referring to Bismarck as the masculine pronoun instead of the traditional feminine she. He believed Bismarck was too powerful to be called she. The man who would command the fleet from Bismarck's bridge was Admiral Günther Lütjens. 51 years old, he would turn 52 on May 25th, in the middle of the operation that would kill him. Lütjens was a complicated figure, a career naval officer who had successfully commanded the Scharnhorst and Gneisenau on commerce raiding operations earlier in 9941. But he was pessimistic about the mission he had been assigned, Operation Rheinübung. He told colleagues he did not expect to survive. According to post-war accounts not fully verified independently, Lütjens had publicly protested the violence against Jews during Kristallnacht in November 1938 and had been noted by the Gestapo for it. He had also insisted that prisoners of war under his command be treated humanely. He was not a Nazi true believer. He was a professional who followed orders, even the ones he disagreed with. Lindemann and Lütjens would clash. Lindemann, the gunnery expert, trusted the ship absolutely. Lütjens, the fleet commander, trusted the mission not at all. Their disagreement would come to a head in the Denmark Strait, and the decision Lütjens made there is still debated 85 years later. The engineers had finished their work. On paper, Bismarck was everything they had set out to build. 19,000 tons of armor, the fastest-firing 15-inch guns on the ocean, a hull that could make 30 knots and survive flooding at both ends, a fire control system with redundancy built into every layer, a torpedo defense that could absorb a hit and keep fighting. Every system reflected the same philosophy. Every philosophy traced back to the same experience. Jutland, close range, flat trajectories, belt armor, turtleback, survival. But the war waiting for Bismarck was not Jutland. The war waiting for Bismarck had torpedo bombers, carrier-launched strikes, radar pickets, and threats that came not from the side, where 19,000 tons of armor stood ready, but from the air, from below, and from the stern, from the one place the genius engineers had left unprotected. The exam was about to begin. On a morning in late May 1941, a lone Spitfire climbed high above the Norwegian coast. It was not a fighter variant. It carried no guns. The reconnaissance version of the Spitfire, the PR-3, had been stripped of weapons and armor to save weight, because what it carried instead was more valuable than any bullet. Cameras, 2 of them mounted in the fuselage, pointed downward through optical glass windows. The pilot was Flying Officer Michael Suckling, around 25 years old, assigned to the No. 1 Photographic Reconnaissance Unit, an elite outfit whose job was to fly alone, unarmed, deep into enemy-controlled airspace, photograph what they found, and get out alive. No escort, no protection, just speed, altitude, and nerve. Suckling pushed his Spitfire above the cloud layer over Grimstadfjord, Norway. Below him, German fighters patrolled the approaches. He had seconds, not minutes, to find his target before someone spotted the contrail and came after him. He squinted through breaks in the cloud, and then he saw her. Even from 30,000 feet, There was no mistaking what sat in that fjord. The silhouette was enormous. A warship, longer than 2 football fields, wider than a city avenue, with 4 massive turret housings visible even at altitude. Bismarck. And beside her, the sleek outline of the heavy cruiser Prinz Eugen, suckling, snapped his photographs and dove away, pushing the Spitfire to its maximum speed before the fighters below could climb to intercept. He made it back to Scotland, with his film canisters intact. Within hours, the photographs were on the desk of Admiral John Tovey, 56 years old, Commander-in-Chief of the Home Fleet, the man responsible for keeping the Atlantic sea lanes open, the convoys that fed Britain, armed Britain, kept Britain alive. Tovey studied the images and understood immediately what they meant. Bismarck was not sitting in port for maintenance. Bismarck was preparing to sail, and if she reached the open Atlantic, the consequences would be catastrophic. Bismarck's engineers had designed her for exactly this mission. Every system aboard the 30-knot speed, the Kopf-Sondershells with 62 kilograms of TNT that detonated on contact, the chemical smoke generator for retreat, the turtleback armor for survival, served a single tactical purpose: commerce raiding. Find a convoy, close at speed. Destroy the merchantman before escorts could concentrate. Vanish into the vastness of the Atlantic. Britain's survival depended on those convoys. 40 million people on an island that could not feed itself. Every ton of grain, every barrel of oil, every crate of ammunition came by sea. If Bismarck reached the convoy lanes, she would be a wolf among sheep, and her engineers had built her to be the most efficient wolf the ocean had ever seen. The chase was on, but Bismarck had an 800-mile head start. Operation Rheinübung Exercise Rhine had begun on May 18th, WWII 941. Bismarck and Prinz Eugen slipped out of Gotenhafen, the Polish port city of Gdynia, and turned north. On the bridge, Admiral Günther Lütjens, 51 years old, 2 days from his 52nd birthday, commanded the task force. He had done this before. Earlier in 941, he had taken Scharnhorst and Gneisenau into the Atlantic on a commerce-raiding cruise that sank or captured 22 ships, totaling over 115,000 tons. He knew the business, he knew the risks, and he was quietly certain he would not come home. Lütjens had told colleagues before sailing that he did not expect to survive the operation. This was not melodrama. It was calculation. Bismarck was the highest value target in the German fleet. The moment she was detected, the entire Royal Navy would converge. Lütjens understood that if anything went wrong, anything at all, the margin for escape was razor thin. Captain Ernst Lindemann, 47 years old, Bismarck's commanding officer, did not share this pessimism. Lindemann was a gunnery expert. He had overseen the ship's trials, watched her guns find their targets with mechanical precision, felt the hull absorb Baltic swells without complaint. He trusted the engineering, he trusted the armor, he trusted the speed. 2 men on the same bridge, looking at the same ocean, seeing 2 completely different futures. One trusted the ship, the other trusted the mathematics of war. They were both about to be proven right and both about to be proven wrong. On May 20th, as the German ships transited the narrow strait of the Kattegat between Denmark and Sweden, the Swedish cruiser Gotland spotted them. Sweden was neutral, but neutrality did not mean silence. The sighting report passed through Swedish intelligence channels, reached the Norwegian naval attaché, and from there, within hours, to London. Bismarck had been at sea for 2 days. The British already knew. On May 21st, the task force anchored briefly near Bergen, Norway. This was the moment for Bismarck to top off her fuel tanks. 7,400 tons maximum capacity. 8,800 nautical miles of range at 19 knots. The numbers were generous, but only if the tanks were full. Lutyens chose not to refuel completely. The reasons behind this decision remain debated. Perhaps he wanted to minimize time in port, where the ships were vulnerable to air attack. Perhaps he believed the operation would proceed quickly enough that full tanks were unnecessary. Whatever his reasoning, Bismarck sailed from Norway without a full fuel load. This decision collided with a design choice the engineers had made years earlier. Bismarck's forward fuel tanks, the ones in the bow section, had no cross-connection valves to the main fuel system. If those tanks were damaged or isolated, the oil inside them could not be transferred to the rest of the ship. It was simply stranded, useless, a design feature that no one had questioned because no one had imagined a scenario where the bow would be damaged and the ship would need to keep fighting across thousands of miles of ocean. Lutyens' tactical decision and the engineer's design choice were two halves of the same trap. Neither was fatal on its own. Together, they would be devastating. Meanwhile, at Bergen, Suckling Spitfire had already taken the photographs. Tovey had seen them. The home fleet was mobilizing, and Bismarck, her captain, confident, her admiral fatalistic. Her fuel tanks, not quite full, sailed north toward the Denmark Strait, the narrow passage between Iceland and Greenland that would carry her into the open Atlantic. She did not know that the British were already moving to intercept. Lutyens believed he had not been detected. He was wrong. The engineers had given Bismarck the finest stereoscopic rangefinders in the world for aiming her guns. But the Fumo 23 radar, the system that should have told Lutyens whether anyone was watching, had an effective range of just 25 kilometers and could track only one contact at a time. No plan position indicator, no battlefield picture, just a single bearing and range to a single target. The engineers had given Bismarck extraordinary eyes for shooting. They had given her almost nothing for seeing. May 24th, 1941. The Denmark Strait, a corridor of grey water between the pack ice trailing south from Greenland and the northwest Oslo. Visibility poor, sea running heavy, temperature barely above freezing. Vice Admiral Lancelot Holland was waiting. Holland was 53 years old, a career officer who had commanded cruisers in the Mediterranean and understood surface warfare as well as any man in the Royal Navy. He had been given 2 capital ships to stop Bismarck, and he intended to close the range as fast as possible. His flagship was HMS Hood, 42,100 tons, the most famous warship in the world. For 20 years, Hood had been the symbol of British naval power, the ship that showed the flag in every ocean, the vessel that foreign dignitaries were brought aboard to be impressed by. She was beautiful, fast, and enormous. She was also 20 years old. A battle cruiser designed in 1916, laid down during the same war that had produced the Battle of Jutland. Her armor scheme reflected the priorities of that era: speed over protection. Her deck armor, in particular, was thin by 1,941 standards. She had been scheduled for a comprehensive modernization that would have addressed this weakness. The war came first. The modernization never happened. Beside Hood steamed HMS Prince of Wales, a King George V-class battleship, modern, heavily armored, carrying 10 14-inch guns in 2 quadruple turrets and 1 twin. On paper, she was formidable. In practice, she had sailed almost directly from the builder's yard. Civilian technicians from Vickers Armstrong were still aboard, working on turret mechanisms that had not been fully debugged. Her crew had barely finished working up. She was, in the most literal sense, unfinished. Holland knew what he was sailing toward. He knew Bismarck's guns were fast and accurate. He knew Hood's deck armor was a vulnerability. His plan was to close the distance as rapidly as possible, to get inside the range where shells would come in flat, where Hood's side armor would matter more than her deck armor. The same logic that had guided Bismarck's engineers. The same lesson from Jutland. But closing fast meant approaching at a narrow angle. And approaching at a narrow angle meant Hood and Prince of Wales could only fire their forward turrets. Half their guns would be pointed in the wrong direction during the most critical minutes of the approach. It was a calculated risk. Holland accepted it. He had no better option. At 5:52 in the morning, the gun spoke. Hood and Prince of Wales opened fire on the German ships. Bismarck and Prinz Eugen fired back. And in the frozen half-light of an Arctic dawn, the system that the German engineers had built, the system that Krupp and Zeiss and the Seesloff 38 computer team had spent years perfecting, went to work. The Zeiss rangefinders locked onto Hood. 10.5 meters of precision optics stereoscopic instruments that merged two images into a single sharp picture, giving range to the target with extraordinary accuracy. The data flowed into the Seesloff 38 fire control computers. Course of the target, speed, bearing, wind, barometric pressure, temperature of the gun barrels from previous firing. The computers adjusted for everything automatically, continuously, faster than any human crew could manage with manual calculations. The solution appeared on the CRT displays. The turret crews loaded the Panzergranate L4.4 armor-piercing, painted blue, 800 kilograms, delayed fuse, 20.3 kilograms of TNT. The guns elevated. The firing gongs rang. Bismarck found the range with startling speed. Her shells began falling close to Hood almost immediately. The system was performing exactly as designed as the engineers had promised it would. Close range, flat trajectory, Zeiss optics, Seesloff 38 computers, Krupp shells, every component doing precise what the blueprints said. At 6:19 minutes after the first shots, a shell struck Hood. The exact sequence of what happened next has been reconstructed from the testimony of survivors and observers on other ships, but some details remain disputed. What is certain is this: a 15-inch shell, almost certainly from Bismarck, though some historians have argued it may have come from Prinz Eugen, penetrated Hood's deck and reached the after magazines. The magazines contained cordite propellant charges for Hood's 15-inch guns. The cordite detonated. Hood broke apart. The explosion was visible from every ship in the area. A column of flame erupted from the battlecruiser's midsection, rising hundreds of feet. The ship's back snapped. The bow section and the stern section each rose separately into the air as the center of the ship disintegrated. Within 3 minutes, some accounts say less, Hood was gone. 42,000 tons of steel, 20 years of legend, and 1,415 human lives, swallowed by the North Atlantic in the time it takes to boil a kettle. 3 men survived. Midshipman Ted Briggs, able seaman Bob Tilburn, ordinary signalman Bill Dundas. They were pulled from the freezing water hours later. Vice Admiral Holland was not among them. 1,415 dead, 3 alive. For one frozen moment, every system the engineers had designed achieved its purpose simultaneously. The Zeiss rangefinders found the target. The Seesloff 38 calculated the solution. The Krupp guns delivered the shell. The shell's delayed fuse let it punch through Hood's thin deck armor and detonate deep inside, exactly where the damage would be catastrophic. If you wanted to point to a single moment and say there, that is what the genius engineers built, it was 6:01 on the morning of May 24th. 1,941. But the same battle that proved the engineers right about fire control also began to reveal the places where they had gotten things wrong. Prince of Wales, despite her turret problems, had managed to hit Bismarck 3 times before retreating under a smokescreen. One shell struck the bow and tore open compartments below the waterline. Seawater flooded in. Fuel oil leaked out. Bismarck began trailing a slick of oil across the surface of the ocean, a visible track that any pursuing ship or aircraft could follow. The forward fuel tanks, the ones with no cross-connection valves, were now cut off system. The oil inside them was irretrievable. Combined with the decision not to refuel fully at Bergen, Bismarck had lost a significant fraction of her operational range in the first minutes of her first engagement. Another hit damaged the compressed air system for the aircraft catapult. The Arado floatplanes could no longer be launched. This mattered because the ship's war diary, the log, and film footage shot during the engagement with Hood had been planned for evacuation by air flown to safety in occupied France. Without the catapult, there was no way to get the material off the ship. The Arados were pushed overboard. The film, the log, the war diary, sources that would have answered dozens of historical questions, sank with Bismarck and have never been recovered. On the bridge, the disagreement between Lutyens and Lindemann came to a head. Lindemann wanted to pursue Prince of Wales. The British battleship was retreating under smoke. Her turrets were malfunctioning at one point. Her only operable turret jammed completely, leaving her unable to return fire. Lindemann, the gunnery expert, saw an opportunity to destroy a second capital ship while she was crippled. The Zeiss rangefinders could track Prince of Wales through the smoke. The C-38 had already proven it could compute accurate solutions. The Krupp guns were undamaged and fully operational. Lutyens refused. His orders were to attack convoys, not to engage the Royal Navy's battle fleet. Every shell fired at Prince of Wales was a shell that would not be available for commerce raiding. Every minute spent pursuing a fleeing battleship was a minute closer to the arrival of British reinforcements. Lutyens was not thinking about the next hour. He was thinking about the next week. And in his calculation, the mathematics of concentration, more British ships converging from every direction would eventually overwhelm Bismarck, regardless of how well her guns performed. Lindemann obeyed. He disagreed, but he obeyed. The debate over whether he was right, whether a pursuit would have destroyed Prince of Wales and changed the course of the operation continues among historians to this day. What is certain is that Bismarck turned away from the crippled British battleship and continued south toward the open Atlantic, trailing oil and bleeding fuel from tanks that the engineers had not thought to connect. Bismarck was hurt, but far from finished. Lutyens separated from Prinz Eugen, sending the cruiser ahead to operate independently and set course for the French port of Brest or Saint-Nazaire, where dry dock facilities could repair the bow damage. The engineer's design was now being tested in a scenario none of them had anticipated. Bismarck was not ambushing a convoy, she was running, and the systems they had built for attack were being repurposed for survival. The oil slick was the most immediate problem. Every mile Bismarck sailed, she left a visible trail on the surface. British cruisers, HMS Suffolk and HMS Norfolk, were shadowing her from behind, track her position with their Type 284 radar. Bismarck's Fumo 23 could detect the shadowers, but the lack of a PPI display meant Lutyens could only see one contact at a time. He knew he was being followed. He could not see the full picture of how many ships were closing in, or from which directions. The fuel situation was deteriorating. Without the forward tanks, Without a full load from Bergen, Bismarck's range was shrinking with every hour at speed. To conserve fuel, Lütjens reduced speed, surrendering the 30-knot advantage the engineers had given him. The hunter was becoming prey, and the prey was slowing down. On the night of May 24th, the first air attack came. Swordfish torpedo bombers from the carrier HMS Victorious found Bismarck in the darkness and launched their torpedoes. One struck the main armor belt amidships, exactly the area the engineers had fortified most heavily. The torpedo belt, 45 millimeters of outer plating, 5.5 meters of layered compartments. Fuel and water in the inner void spaces absorbed the detonation precisely as designed. The shock wave was dampened. The shrapnel was contained. Damage was minimal. Bismarck shrugged off the hit and kept moving. The torpedo defense engineers had passed their exam. The system they had designed using lessons from Jutland and 20 years of theoretical work had just proven itself against a real warhead in real combat conditions. Bismarck's sides were as tough as the blueprints promised, but the sides were not the part of the ship that was in danger. Then Bismarck vanished. Late on May 25th, the cruiser Suffolk, which had been tracking Bismarck on radar for hours, lost contact. The target simply disappeared from the screen. One moment, the blip was there. The next, it was gone. For nearly 32 hours, the Royal Navy had no idea where Bismarck was. The engineer's hull design was partly responsible for this disappearance. That long, narrow ocean liner shaped the hull that bled 65% of its speed end in a hard turn but sliced through the Atlantic like a racing yacht on a straight course, was making Bismarck very difficult to find in the vast grey expanse of the North Atlantic. She was one ship in 1 million square miles of water, and she had broken free. 32 hours. In that window, Bismarck could have reached the air cover of Luftwaffe bombers based in France. She could have made port. She could have disappeared into the Atlantic for weeks, refueled from a supply ship, and re-emerged to savage a convoy when the British had given up the search. The engineers who designed that hull, fast, efficient, hydrodynamically refined, with the bulbous bow borrowed from the ocean liner, Bremen had given Bismarck the tools to escape. And then Günther Lütjens made the mistake that killed him and everyone aboard. At approximately 10:30 on the morning of May 25th, Lütjens composed a long radio transmission to Naval High Command in Berlin. A detailed situation report: damage to the bow, fuel status, course, and intentions.